Welcome to this presentation video on the research paper, Learning to Discover at Test Time. Today we dive into a mindset shift in how we use a large language model, or LLM. Instead of endlessly prompting a frozen model for a better guess, we let it learn during the test problem by updating its own weights. This is based on UCSD et al. 2026, with collaborators across Stanford, NVIDIA, UCSD, and Together AI. Here is our roadmap. First, we will unpack the frozen brain problem. Then, we will introduce the test time training discover idea, or TTT-Discover. Next, we will cover 2 key tricks that make it work in practice. Finally, we will walk through results in math, kernels, coding, and biology. Let us get started. Now look at this slide. Architect's daughter, thinking on the frozen brain problem. The metaphor is brutal on purpose. A standard LLM at test time is frozen. Its weights do not change. So across attempts, it has basically 0 short-term memory. Notice how that breaks intuition. You would expect 10,000 tries to make it smarter. What's interesting here is test time compute tricks, like best of n. You sample a bunch of answers and pick the best, but each attempt is another independent guess. Even after 9,199 failures, the model does not learn from them. Why does this matter? On truly out-of-distribution problems, search can burn massive compute without building any new capability. Now look at this moment. The architect's daughter realizes, wait, I need to update my synapses. Notice what changed, not the effort, but the strategy. Instead of retrying the same approach harder, she treats the mistake as information and rewires how she thinks. What's interesting here is the blunt line on the slide. The answer isn't in the training data, the book. Have you ever hit a problem where every example you studied suddenly feels useless? That is because discovery is not lookup. It is adaptation. This builds on what we saw earlier. We do not just search the space, we learn. Each failure becomes new, problem-specific training data that guides the next attempt. Now look at this shift in mindset. TTT-Discover refuses to keep the model frozen at test time. Instead, it actually runs reinforcement learning during the test itself. Why does this matter? Because the test problem stops being a one-shot exam and becomes an environment the model can interact with. Notice how they approached it. The model proposes a candidate solution. That solution gets evaluated by the task's scoring or verifier, and the outcome becomes feedback that drives real weight updates. So every attempt is not just a guess, it's experience. What's interesting here is the distribution shift is no longer a threat. That out-of-distribution test case becomes the new training distribution on purpose. The goal is continual learning, not for generality, but to land one specific standout solution. Now look at this plot. On the left, standard RL climbs toward high average reward. Notice how they approach the problem. Safe, consistent, repeatable. And the caption basically calls it out. Safe, consistent, boring. Why does that matter? Because discovery is not a job interview where you need to perform well every time. On the right, TTT-Discover looks messy. Attempt after attempt that feels like garbage, 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 until suddenly, Nobel Prize. What's interesting here is the objective shift. Scientific progress does not care about the mean reward. It cares about the maximum reward achieved. The single outlier that changes everything. Okay, secret weapon, number 1, is the entropic objective, and the whole point is to reshape the loss so the best outcomes in a batch get amplified, while the mediocre ones barely matter. Notice how they say it aggressively, favors the best, and ignores the rest. That is the opposite of averaging everything together. What's interesting here is the adaptive beta. Think of beta as a risk factor knob. If the model starts playing it safe, beta gets turned up, which makes high reward attempts count way more, nudging the policy into bolder exploration. Why does this matter? Typical training smooths you toward reliable average behavior. This objective concentrates the learning signal on rare, high-reward trajectories, exactly where breakthroughs live. If you're finding this interesting, check out our blog post, linked in the description for more details. Then secret weapon number 2 Why walk the first 5 miles again? That is the pain of standard search state reuse. You generate an attempt, hit something promising, and then the next run starts from scratch, like none of that progress mattered. What's interesting here is the buffer idea. Instead of throwing away partial wins, we save states. Think partial code, half-finished proofs, or a sketch that almost works, and keep them on the shelf. Then new attempts don't begin at zero. They begin from a checkpoint that already explored useful terrain. And here's where the PUCT framing becomes the secret weapon. We prioritize paths that showed any greatness, even if a state is inconsistent or imperfect. It might be one tweak away from a breakthrough. Reuse those states and you reach deeper solutions faster. So, here is the TTT loop. Notice how they approach discovery like an assembly line. First, you generate a huge batch of rollouts, basically many different solution attempts. Then you evaluate them, and only the useful states get saved into a buffer, so the system can reuse the best stepping stones instead of starting from zero every time. After that, you do training updates on what worked, and you repeat the cycle. What's interesting here is the concrete scale, 50 training steps and 512 rollouts per step. Have you ever wondered why this matters? Because it's not free. The slide flags about $500 of compute per problem, but it's aimed at producing one standout solution, not an average one. Now look at this headline comparison. On the Erdős minimum overlap problem, the old state-of-the-art from Alpha Evolve sits at 0.38094, and TTT-Discover nudges it to 0.30876. That looks tiny, right? But in problems like this, shaving off a few 10,000 can mean you found a fundamentally better construction, not just a lucky tweak. Notice how they describe it. So polite, so symmetric, ugly, but effective. The key insight here is that the winning answer is not a clean, human-friendly, symmetric pattern. Instead, TTT-Discover uncovers a 600-piece asymmetric construction, basically a massive irregular arrangement that still scores better on the metric. What's interesting here is where it searched. It explored regions humans typically would not look, and it paid off. Now look at this bound shift. The previous best from Theta Evolve had C1 less than or equal to 1.5314. TTT-Discover nudges it down to C1 less than or equal to 1.5026, and that tiny change is a new state of the art. Why does a difference in the fourth decimal place matter? Because in inequality chasing, you are not just tweaking a number, you are usually finding a genuinely different certificate, a new construction, or a new region of the search space that older methods simply did not reach. What's interesting here is how they approached it. They started from scratch, yet still beat systems that were fine-tuning the existing best solutions. That is a strong signal the method is actually discovering, not just polishing, and here are the results. The best human TriMul kernel on an H100 clocks in at 1371 microseconds, and TTT-Discover comes back with 1161 microseconds. That is about a 15% speed up. Not a rounding error, a real win. What's interesting here is how it got there. Instead of treating the kernel as a fixed recipe, the model started making bolder, low-level choices, fusing operations, so data stays in registers longer, and switching to reduced precision, FP16, in spots where humans were too cautious. Have you ever wondered why people hesitate there? Because FP16 can bite you if you pick the wrong place. But the model learned where it actually pays off on this hardware. This is discovery in code form, iterating until the trade-offs match the GPU. Don't forget to check the description for additional resources on this topic. More results, competitive coding, and single-cell biology on the same results slide. On the coding side, the claim is bold. This approach would have placed first on AtCoder's heuristic contests, including AHC39 phishing and AHC8, the Apple economy. Notice how those contests don't reward elegant theory. They reward whatever scores best under a simulator. So the benchmark is brutally practical. Generate an algorithm, run it, get a score, iterate. What's interesting here is the biology benchmark uses the exact same loop. In single-cell RNA-seq denoising, the method beat magic by improving mean squared error, basically closer reconstructions of the underlying gene expression. Why does this matter? Because across both domains, the environment is the same. Propose a solution, score it, learn from it. An ablation is basically the scientific way to answer, do we really need the fancy stuff? You take the full method, then remove one ingredient at a time and watch what breaks. Notice how they approached it. Compare standard RL, then add reuse. Then the full test time training setup, and finally, T-Discover. What is interesting here is the failure modes. Patrick Hand's note nails it. Without test time training, the run stagnates. It stops getting better because the model is not actually learning from its attempts. And without the entropic objective, improvements are painfully slow because the agent plays it safe. Punchline, you need both. Risk-taking from the objective and deep exploration from state reuse. The researchers did not lean on some proprietary closed mega model. Notice how they explicitly chose GP Topo OSS 120B, an open source model. Why does that matter? Because it makes the whole discovery pipeline more accessible and easier to reproduce, instead of being locked behind a private API and a massive budget. And the cost number is the real gut check. Only about $500 of compute per problem. Think of that as a practical per discovery budget, not a moonshot research grant. What is interesting here is the takeaway. You do not need a supercomputer, you need a smarter process that learns during the attempt. To wrap up this presentation, here are the 3 big takeaways from research paper. First, do not just search, learn. Instead of prompting harder, update the weights so the system actually improves on the task. Second, for discovery, average is bad and max is good. You want to maximize the outlier signal that reveals something new. Third, open models plus test time training can be dangerous. Lie good. Because adaptation at inference can unlock capabilities you did not see at training time. That is the core idea. Stop brute forcing prompts and start building a system that gets better while solving the problem. Thank you for watching, and a huge thank you to the authors for their amazing research. If you want to read more, our detailed blog post, complete with slide deck, quiz, and flashcards, is available at emergentbehaviors.com and linked in the description. Let me know your thoughts in the comments and where you would apply test time training. Thank you for your time, and I'll see you in the next video. Bye.